Welcome to Web Handling. My name is Dave Roysum. I am super excited to start a new series on the productivity of ReWinders and other converting equipment. In this first clip, we will discuss how to predict productivity. In the next clip, how to measure productivity. While this might seem backwards, that measuring should be easier than predicting, there are many reasons for this order. One reason is that knowing what is required to predict productivity helps you understand how to measure productivity, as well as how to interpret those measurements. The motivation for analyzing productivity is obvious: money. However, we first need to understand the elements of productivity before we can minimize rewinding and converting department costs. One large cost area is labor. It can cost upward of $250,000 for each 24/7 position. Of course, your people aren't paid that much. However, consider that each 24/7 position takes 4 full-time workers to cover. So take that yearly wages of 4 hourly workers times 1.5 to cover benefits, and you get costs that are notable. Another notable cost includes waste, because each additional process step adds more waste. One example is the waste at the top and the bottom of every wound row. There are other sources of waste as well. Also, equipment is expensive. A rewinder may cost $20,000 to $20 million. Converting the equipment can even cost more. To this initial cost, we also must add ongoing maintenance costs such as parts and labor. Other costs that vary considerably include accidents, which are known in the legal system as personal injuries. Winders, whether rewinders or the winder at the end of an R2R converting machine, often have the worst track record of injury of any of the machines in a plant. If you are good and are lucky enough to escape serious injury, you have just saved the company on the order of $1 million. To understand rewinding and converting department costs, we must first be able to calculate and measure productivity. In rewinding, this is known as time cycle analysis. The elements of the cycle include acceleration, run, and deceleration of the winding portion. The elements also include the downtime needed to change the rolls. These simple time cycle elements are presented in this clip. In the next clip, we will discuss stochastic elements, such as grade change, maintenance, and upsets. The heart of a rewinder time cycle is the speed versus time graph. Here we show the heartbeat of an athlete, strong and steady. In this example, we are rewinding 3 sets per master roll. Of course, the technique would apply to any number of finished sets per master roll, from 1 to 100. Note the repeating elements: accelerate, run, and decelerate, followed by a finished roll set change. At the end of the 3 sets, we must add time to change out the master roll. The individual times for each of these elements can be calculated and summed to give the time to process 1 master roll. Since we must know the length of the master roll, the average speed or productivity of the rewinder is the length divided by the time per master roll. This average speed is like the problem of the tortoise and the hare. The rewinder varies speed like the rabbit, but must keep ahead of the steady input from manufacturing, like the tortoise. The acceleration rate is set by the machine builder. It is around 30 meters per minute per second for many ReWinders, but noticeably slower for most other R2R converting machines. Run speed is typically 50 to 80% of design speed, though there is notable variability here. For example, salvage winders tend to run quite slow, perhaps due to poor oversight, or perhaps do you want it good or do you want it fast fallacy. The deceleration rate is set by the machine builder and is around 40 meters per minute per second for many high-speed ReWinders. The rate here we are referring to is the normal stop, where tension is maintained at least to zero speed. An e-stop is an entirely different matter. In an emergency, every torque element goes into maximum braking effort without any attempt to maintain tension or coordinate the stop. Machine builders often size the torque elements for a minimum of 100 meters per minute per second. The runtime is back calculated from roll footage and the amount of material wound during the acceleration and deceleration. The area under the speed versus time plot is the footage in the roll. To the winding time, we add the time to change out the set of finished rolls to get the total time for one set. Now, we merely repeat the process for each of the remaining of the finished roll sets in a master. To that, we finally add the time to change out the master. All of these calculations are done with simple high school math. Thank you so very much for allowing me to share simple time cycle calculations. In the next clip, we will add additional time cycle elements as well as discuss how to measure productivity. See you next time.